another one to do. Okay. So, so we're looking at generation M, which I believe probably is the millennials, right? You guys are what? Gen what?
Z.
Gen Z? And when was Gen Z, when were they born? Do you know?
I think it's like ages like 23 to something like, I don't know. I think it's like late 90s to early 2010s maybe. I'm not 100% sure.
Gen Z. What is Gen Z age range? 6 to 24, 1997 to 2000. That's very good, Emma. Very good. You're on top of it here. You're like super hip. I'm like totally out of it. Yeah, I don't know what's going on with this stuff. All I know is that I'm a baby boomer. You know, I didn't even know they have a name for my parents. They're like called the traditionalists. That's weird. But I also learned that there is a generation after Gen Z. Well, I would hope there is. You know, I hope you aren't the last generation. You know, but what is after Gen Z? Let's see. After Gen Z, that's called Generation Alpha. Where do they get this stuff? Who's making this up? Who's got the copyright on this nonsense? That's ridiculous. They're born after 2010, so they're like babies. But it says here, this cracks me up. They're on track to be the most transformative age group ever. Well, what does that mean? I mean, really, you know, some people, how do they? Who gave you the right? You know, at any rate, okay. So we're in generation M, Gen M in this problem, because that's the I got to get the there we go. Okay, generation M. And we remember that our sample of 2032 children, or young adults, let's call them, 68% had a television in their bedroom. So this was our N. This was our P hat. And we're going to construct a 95% confidence interval for pi. We want to be 95% confident. Now, we are not going to use the empirical rule. Empirical rule would just be 2 standard deviations. It would be a piece of cake, right? But we're gonna use our methodology and calculate a little more accurate 95% confidence interval. So let's kind of get ourselves a page here. And so I want to draw a picture. So and Imani is the one person who's absent today, and of course she comes up out of the magic ball. So Emma, what's my picture going to look like?
Unimodal and symmetric.
How do you know that? You are right, but how do you know that for sure?
Well, okay. Honestly, I was just guessing because everything we do lately has been unimodal and symmetric.
Well, that was a good guess. All right. It is going to be unimodal. It is going to be unimodal and symmetric, but we know it is going to be unimodal and symmetric because P hat times N is greater than, see, this is proportions, right? Is greater than 10, and 1 minus P hat times N is greater than 10. N is 2032, P hat's 0.68, clearly greater than 10. 1 minus P hat would be like 0.32 times 2000 something is also going to be greater than 10. So this is the condition we have to meet in order to say that our diagram is going to be unimodal and symmetric, right? Is everybody okay with that? Okay, so we know it's going to be unimodal and symmetric, and I'm going to take that out. And so Isabella, what's going to be the center of this?
It's going to be the mean.
Well, yes, but I want a number. Here's the problem. Look at the problem. Not sure?
Yeah, I'm not sure.
Okay, hang on. You have to be sure on this. Okay, so we're going to ask Karina, what's going to be the center?
Our center, isn't it gonna be 0.68?
If you take away the question mark, it'll be 0.68. It's going to be like this. It's going to be 0.68 exclamation point. It's not going to be 0.68 question mark. Okay, 0.68, 0.68. Now, Isabella, I just want to be clear here. That is not the mean. That is our p hat. That is our proportion for the sample, right? Means are with quantitative variables. Proportions are for categorical variables. And if you remember, this is a categorical variable because it's television set, yes or no. Good? Yes, okay. Now, we calculated the standard error, but let's just do it again so that everybody can follow here. The standard error is going to be the square root of p hat times 1 minus p hat divided by n. So it's going to be the square root of 0.68 times 1 minus 0.68 divided by 2032. So let's just kind of do that here, even though we know what it's going to be. Let's do it anyways. So I have a 0.68 times 1 minus 0.68. I'm going to divide that by 2032, my sample size. And then I'm going to take the square root of that. And I get 0.01. So my standard error, which is similar to the standard deviation, is 0.01. So that made this very easy to draw. 1, 2, 3, 1, 2, 3. And here is my p hat. Here is 1 standard error, 2, 3, -1, -2, -3. Now, if I was just using the empirical rule, I would say, well, let's actually fill in the numbers here. I should do this. So 0.01, so this is 0.69, 0.70, 0.71, 0.67, 0.66, and 0.65. Okay. If I was just using the empirical rule, I would say, well, between -2 and 2 is 95%. And a lot of times it's fine to use the empirical rule. But in this case, we cannot use the empirical rule. We're not allowed to because they wanted to get a little bit more exact. So I'm going to take that away. And I'm just going to tell you that 2 standard deviations on either side is a little bit more than 95%. So I'm going to just make my lines right in here and right in here. So between these two is 95% confidence. And what I need to get is this number here, this proportion right here, and this proportion right here. That's going to make up my confidence interval. I will stop. Question? And we're doing okay? All right. Well, if I want to find this number over here, and I'm going to look at the one that's on the positive side. What do I need to find that number? I can tell it's between 0.69 and 0.70. Can you see? It's going to be between 0.69 and 0.70. It's going to be between those two numbers. In order to find it, what do I need to find it? Brooklyn, do you know?
I don't know how you find it.
Okay, that's fine. We're going to do it in just a second here. Let's give one more person a chance. Emma, do you know?
Is it Is this the thing where we take it and do like the 50 and like the half?
Yep.
Okay, so, and then you find like the INV norm like on your calculator?
Okay, but so you're right on target. You know the process here. When we're finding the inverse norm, what is the argument of an inverse norm?
Um, is it the percentage?
It is. It's the percentile. So what I need to find here is first I need to find the percentile, and that is going to give me the z-score at that spot. And once I find the z-score, then I can use z equals x minus x bar over s to find this exact number right there. Okay, so I'm going to do what Emma told me to do here. I'm going to take my 95%, I'm going to divide it in half. That would be 47.5 on this side. And let's go to there, all the way to the red line. And 47.5 on that side. Is everybody clear on why that's the case? Is there a question? Ask me a question. Put it in the chat. You can unmute. Okay. So I got 47.5 on both sides of the middle here. So I'm going to say, okay, I know that over here is 0% and over here is 100% of the data. So if I go from 0 to the middle, that gets me 50%. And if I go from the middle to the line that I'm looking for, that gives me 47.5%. So I know that this percentile is the 97.5 percentile. 50 plus 47.5. Are we okay with that? Okay, I'm going to say it in a different way, just to kind of give you another way that maybe comprehend it. The total amount of data underneath the curve is 100%. Everybody's okay with that, I'm sure. And I'm looking for 95% confidence. That leaves 5% left, correct? Well, 5% is this side over here plus this side over here because the thing's unimodal and symmetric, right? So I got 2.5% over here, that's half of 5. And I got 2.5% over here, which is half of 5. And if it's 100 all the way to the end, and I back up 2.5%, once again, I'm at 97.5%. So two different ways to kind of look at it in your in your diagram. Well, let's find the z-score then. So I'm going to go second distribution, 3 for inverse norm, and I'm going to put in 0.975. Do not put in 0.95. This is not the 95th percentile. It is the 97.5 percentile. So I'm going to close my parentheses. I'm going to hit enter. And I find out that the z-score for this is equal to let's call it 1.96. That's my z-score. So if I know my z-score, then I'm going to use my z equals x minus x bar over s to find out, well, what is that exact number right there? So I go 1.96 is equal to x minus 0.68, that's right there in the middle, divided by 0.01. So I'm going to multiply 0.01 on both sides, and I get 0.01 times 1.96 is equal to x minus 0.68, because those kind of cancel out. And then I'm going to add 0.68 to both sides. So I get 0.68 plus 1.96 times 0.01, which equals 0.68 plus 1.96 times 0.01, 0.696. So the number here, let's erase my question mark. The number here is 0.6996. So that's the upper bound of my confidence interval. Now, if I want to find the lower bound, now just to kind of reiterate here, what I'm doing here is, as I had a z-score of 1.96, that's telling me how many standard deviations I am away from the mean. So I take, if I say I'm 1.96 standard deviations away from the mean, and a standard deviation is 0.01, then that's where I get this 0.01 times 1.96. And then I add my 0.68 to both sides, and that gave me my number of 0.6996. But like Emma said in the beginning, even though she was just guessing, it's unimodal and symmetric. So this is going to be the exact same z-score, except it's going to be negative. It's going to be a negative 1.96. So I'm going to do the same thing. I'm going to go, let's use a different color. I'm going to go 0.68 plus negative 1.96 times 0.01. And that equals, so I'm going to go here, I'm going to go 0.68 minus 1.96 times 0.01. And that gives me that number of 0.6604. So this number over here is 0.6604. So my confidence interval is 0.6604, 0.6996. I am 95% confident that the actual population parameter, that the actual proportion of young people that have televisions in their room is somewhere between 0.6604 and 0.6996. I am 95% confident. So that is pretty damn cool. That is pretty cool that I can say that. Is there a question? You're sure? Okay, so now I'm going to show you something else about this. Watch carefully. This is magic. P hat plus or minus the z-score, which this particular z-score is called a critical value, times the standard error. So this formula here comes from our basic z equals x minus x bar over s. It's just a different way of putting it. So when I want to find my confidence interval, I need to find the critical value, that is the z-score for the percentile that I'm looking for, and then go take my center plus or minus, watch my hands, plus or minus how many standard deviations I am away from the mean. Pretty cool. Pretty good. Questions? No, we're making sense. Okay. I'm counting on you. I'm really counting on you to speak up if I'm not making sense. All right. So it says calculate the width of this interval. Well, just so we know what they're talking about, I'm taking a tangent right here. If I had a number line, so here's 0, 1, 2, 3, -1, -2, -3. So if I want the width from, say, -2 to +1, well, I would go 1 minus -2, and that would give me 3. And sure enough, that is the width of this interval, 1, 2, 3. That's pretty straightforward, isn't it? Okay, so if I'm looking for the width of my confidence interval, here we go. I'm going to take my rightmost value of 0.6996, so 0.6996, and I'm going to subtract my leftmost value, 0.6604, 0.6604, and I'm going to, whoa, view, size, medium, that's better. So 0.6996 minus 0.6604. The width of this confidence interval is 0.0392. And if I want the half width of this interval, well, that's just going to divide that by 2. So I'm going to divide that by 2. And I get 0.0196. Well, now that's an interesting number, 0.0196, because that looks to me like my critical value times my standard error. My critical value was 1.96. My standard error was 0.01. That equals 0.0196. So the half width of the confidence interval, which we can also determine by this part of the formula, has a name. It is called the margin of error. And again, I mean, it's not really an error, just like the standard error isn't an error, but that's the terminology that we use. And what it's saying is this. Here's my distribution. Here's my 0.68. Here was my 0.6996. Here was my 0.6604. And what it is I'm saying that pi is equal to 0.68 with a margin of error, MOE, a margin of error of plus or minus 0.0196. You will see this if you look in the newspaper or when you read a survey, a political candidate running, they'll say, so-and-so has, 64% of the vote, with a margin of error of 2%. Have you seen that before? And that's what margin of error is. It's just taking, how confident do you want to be? And it's saying, okay, well, I can be mistaken by that much on this side and that much on that side, that's my margin of error. Margin of error is always a positive number. So it's always the half width on this side. Okay, and we'll say plus or minus the margin of error. But margin of error is just equal to that. Look at all these terms you're learning. You've read them and you think, well, where did they get that from? And now you know. You're so knowledgeable. You should use this on your parents. You know, when they're reading a survey, you're talking some politics in over the dinner table, then they say, oh, well, you know, so and so has a 68% chance of winning. You say, what's the margin of error? And then they say, well, well, you know, and you don't know the margin of error. Well, how confident are you in that number? See, so you have some leverage here now. Of course, if you and your parents agree politically, then that really doesn't matter, you know. But okay. No, we did that. Of course, it looks familiar. Okay, we talked about the technical conditions. We really shouldn't have even started the problem. I don't know why this is all the way here at point I, because before we even start the problem, we need to go p hat times n is greater than 10, and 1 minus p hat times n has to be greater than 10. How would I expect a 99% confidence interval to differ from a 95% confidence interval? I'm going to ask that question, magic bullet. How would I expect it to be different? Alexis.
Would there be a smaller chance for marginal error?
For a 99% confidence interval?
No, it'd be greater.
It'd be
There'd be a
greater.
greater chance of error.
That's right. Think about the target example, which I just made that up yesterday, and I think it's really good. You know, I am 95% confident I can hit that target. I'm 99% confident I can hit that target. It's bigger. It's easier to hit. You know? Yeah. Okay. We're not going to determine a 99% confidence interval. I think you guys know how to do that. Are you comfortable with this? You okay with this process? You know how you can become more comfortable with this process? Yes, you do. Practice problems. That's right. Okay. Okay, so based on these intervals, so we had a 95% confidence interval, 95% CI confidence interval, not crime scene investigation. I would do if I wasn't having fun. All right, so here, let's just look at our diagram. That's the easiest way to do it. Here is our diagram, okay? I know there's a lot of stuff around it, but you can see the basic diagram. It is in green, okay? Is it plausible? That means likely, okay? Is it likely or plausible that the actual population parameter, the actual proportion of young people that have televisions in the room is 50%, is 0.50? Looking at our diagram here, is that plausible? Is that reasonable? Is that a reasonable thing to guess? Caitlin, what do you think?
Sorry, I was trying to write down the diagram. Could you repeat the question?
Yes, I can. Can you see? You can see the diagram though, right?
Yeah, sorry, I was just trying to copy down the numbers.
Not a problem. Not a problem. The question is it plausible that the actual population parameter, the actual proportion of young people that have television in their rooms is 0.50? Is that plausible?
I don't think so.
I don't think so either.
Yeah.
No, it's definitely possible, right? I mean, anything's possible, right? But is it plausible? No. I mean, 0.50, I mean, that would be like way, that'd be like 8 standard deviations away from the mean. Very unlikely. Very, very unlikely. Okay. What about 3/4? Is that plausible? Abby, is that plausible that 3/4 of young people have a television in their room? Is that plausible?
I'm gonna say yes.
Why are you going to say yes?
Because
What is 3/4 as a decimal?
0.75.
Okay. Now you want to rethink your answer here?
Oh yeah, no, because it doesn't fall within the 0.75. So
No, it's nowhere. It's not 95% confident. It's like way out here. Do you see what I'm saying here? It's like, I don't know, 6 standard deviations in the wrong. Very unlikely. Possible, not really very likely. Not really. You get it? Okay. Okay. What about? Oh, let's pull somebody else. Alondra. What about 2/3? Is that plausible? 2/3?
Yes.
Yeah, I think so too. 2/3 is like 0.67, huh?
Right.
Yeah, and that's within our 95% confidence interval. Yeah, that's probably even closer than 95%. That's probably like a 90% confidence interval. Yes, makes sense? Pretty good? All right, good. All right, so we will start with this problem on today's Wednesday, on Friday. All right, we're going to do some practice problems. We're going to do this problem because we're going to divide it up between boys and girls, which would be interesting, right? Because we got a 72 a p hat and a 64 p hat, and you're going to have to determine a 95% confidence interval for both of them. And then we're going to do oh yeah, that's a good problem. And then we're going to do another problem. I don't know whether we'll finish them both on Friday, but another problem with kissing couples. So yeah, okay. So like 10 minutes extra for what is it? Is it break time or? Yeah, it's break time and then it's period 5 and then it's lunch. So, okay, everybody good? All right. No celebrities as your clients. Remember that. Okay. All right. See you later.
Thank you.
Thank
You're
you.
welcome.
Mr. Jenkins, I was wondering if I could ask you a question regarding period, like our